So last week we were looking at evaluating definite integrals using the first fundamental theorem of calculus. That was how to take a definite integral written in this form. How do you evaluate the definite integral from a to x of f of t dt? That would be a question we could answer using the fundamental theorem as you reviewed with a second ago. The second part adds on a little bit more. The derivative with respect to x, d dx, of the definite integral from a to x, where if a is a constant, some constant a to x of f of t dt is equal to just f of x. This puts a couple different concepts together. One of them namely being that what happens when you take the derivative of an antiderivative? Just cancels out, right? Geometrically speaking, what does the definite integral tell us? We graphed these regions a minute ago, or on our last quiz. It's the area under the curve. Isn't a definite integral geometrically just the area under the curve? This would be the rate of change in the area under the curve from a geometric perspective. The rate of change in that definite integral, or rate of change in the area under the curve. Okay, let's say for a minute that we have the definite integral from 0 to x of cosine t dt, not dx. So he's writing dx, let's put dt. You just said that this definite integral evaluates the area under the curve. So let's graph what that might look like. I graph cosine, -1 and 1. So x really represents any value I want it to be. X can take on any value that I want it to be. If x is equal to pi over 2, this is the definite integral from 0 to pi over 2 of cosine t dt, whose area would be given by that region, right? What if we change x to be pi over 3? Well, it's going to accumulate more area out to say pi over 3. So it would be the positive portion above the x-axis, but then take away this portion below the x-axis for our definite, minus that negative area below the x-axis. These are questions that are used by first fundamental theorem of calculus. Let's evaluate this by the first fundamental theorem of calculus, just to kind of see how the first part leads into the second part. What you just practiced. Let's find the antiderivative of cosine t. Value between 0 and x. Now my first fundamental theorem, plug in x, plug in 0 to take the difference. What first fundamental theorem says is, all right, this inner portion, the definite integral from a to x of f of t dt, as we applied to this example, really got me this far. Now the next part, the second part of this fundamental theorem says, what happens if I take the derivative of what I've worked out using from the first fundamental theorem? What if I take the derivative of what I worked through using the first fundamental theorem of calculus? So if I take the derivative of this definite integral, it's the derivative of sine x minus sine of 0. just take the derivative of what I worked through using the first fundamental theorem of calculus. I evaluated the first part using first FTC. I take the derivative for the second part of that fundamental theorem. What's the derivative of sine x? What is the derivative of sine? Someone just said it, yeah. Not negative cosine. That's the antiderivative of sine. What's the derivative of sine? Just cosine, right? What's the derivative of the sine of 0? What's the derivative of sine 0? What is the sine of 0? It's actually a number. What is the sine of 0? 0. Isn't the derivative of a constant always 0? The definite integral from 0 to x of cosine d dt. I take the derivative of that. It just cancels out. I evaluated the first part by using first fundamental theorem of calculus as the definite integral of sine of t from 0 to x, sine x minus sine 0. That's the derivative of sine x minus sine 0, or just cosine x.
Why did we do the derivative of minus
Second.
Why did we do the derivative of sine x at the bottom instead of the antiderivative?
Because the second part of the fundamental theorem says take the derivative of these antiderivatives, and it just cancels back out to the original function, right? That's kind of one key aspect of the first fundamental theorem of calculus. If I differentiate an antiderivative, does it just go back to the original function?
Yeah.
Okay. What's another geometric aspect of some of these definite integrals? What would this tell me? The definite integral from 0 to x of cosine t dt geometrically refers to what? Area under the curve, right? So if I want to find the area under the curve from 0 to, say, pi over 3 of cosine function, I want to find the area between 0 and pi over 2 of cosine t dt. Now just change your x value to pi over 2. The area under cosine from 0 to pi over 2 is just the sine of pi over 2. If I go all the way up to pi, the area under the cosine function from 0 to pi is simply just sine pi. These definite integrals represent an accumulation of area based on whatever x value you have in mind. The rate of change in that accumulating area is just equal to the original function. The derivative or rate of change in that accumulated area just gets back to the original function. Because wouldn't a derivative of the antiderivative just cancel back out to the original function? The first part's evaluated using the first fundamental theorem. But then once you take the derivative, this second part goes away. The derivative of sine x is cosine x. What's the derivative of sine 0? 0. Well, if this bottom thing is always a constant, and I plug it into a function, wouldn't this just always give you some constant whose derivative is always going to be 0? Let's pull up some practice. Let's try a couple other ones up on the board. We got down through, I want to say 19. I should pick up with 20. Use the second fundamental theorem of calculus to find f prime of x if capital F of x is equal to the antiderivative of negative 2 to x of t squared minus e dt. I want to find f prime of x. For f of x, given by the antiderivative of negative 2 to x, t squared minus 2t t. What we're asked to do is find the derivative of this function. So I need to find the derivative of the antiderivative from negative 2 to x of t squared minus 2t dt. These seem more complicated than they really are. According to the notes up on the board, shouldn't this just cancel itself back out again? The derivative of the antiderivative should just be what? I take the derivative of an antiderivative. It gets back to what? It's the original function. But it will be in terms of x. It's going to be in terms of function f of x. So this is really just x squared minus 2x. Change the t's to x's for your answer. And why though? Let's evaluate this using both of the two parts of the fundamental theorem. I'll use the first fundamental theorem to evaluate the inner portion. What's the antiderivative of t squared? I'll say it once. T squared, what's its antiderivative? 1/3 t cubed. How about minus 2t? Between negative 2 and x. Evaluating this using the first part of the fundamental theorem. Now plug in x, plug in negative 2. So 1/3 x cubed minus x squared when I let t become x. Minus, I'll substitute in negative 2 for t. Negative 2 to the third is negative 8. 1/3 of negative 8 would be negative 8/3. Minus negative 2 squared. Negative 2 squared is 4, so minus 4. Negative 8/3 minus 4, that's negative 8/3 minus 12/3, which is negative 20/3. Because of the negative out in front, I think it'll be a positive 20/3. Okay, let's look at this from a geometric perspective first, that geometric application I mentioned. What does the definite integral tell you about a given function? Area under the curve. So what if I want to find the area under t squared minus 2t from negative 2 to 1? What do I plug into this function? 1. What do I want to find the area from negative 2 to 5? What do I plug into this function? 5, right? It's an accumulation of area given by this function. This part right here, we worked out using first fundamental theorem to get this equation. Now, what happens if I take f prime of x? That would be the derivative with respect to x of 1/3 x cubed minus x squared plus 20/3. To be what? Squared minus 2x. That's another important application of the second fundamental theorem. Besides area, we talked about with area, the derivative of the antiderivative just cancels out. When I take the derivative of what I just anti-differentiated, because this last number is always going to be a constant, whose derivative is 0, don't you always get back to where you start? rate of change in that accumulation of area is just given by the same original function. The rate of change of our derivative in our accumulating area is just given by the original function. Those seem a lot harder than what they actually are. You just basically write it in terms of x for your final answer. Let's see, maybe let's try 25. I got 25 up on the screen here. Let g of x be equal to the definite integral from 0 to x of f of t dt, where f is the function whose graph is shown in the figure. So I have the graph of f below. G of x represents the definite integral from 0 to x of f of t dt. Geometrically, what does this apply to? What does this refer to? Area. So on part A, it asks us to find g of 0, g of 2, g of 4, 6, and 8. Well, how could I find g of 2? Oh, zeros first. Let's do 0 first. How do I find g of 0?
Plug in
0, 4, x. G of 0, let x become 0. So substitute in 0 for this x here. What's that obviously equal to? The definite integral of 0 to 0 of anything. Why? It's the area of nothing, right? There's the upper bound and lower bound are the same. Right? Let's try another one. What would g of 2 be? That'd be the definite integral from 0 to 2. So I'm going to accumulate more area because I have a lower bound of 0 to upper bound of 2. Read that graph. What do you think? I think you're going to do your best to estimate it. Just kind of count those squares. I see 2 whole squares and about 2 squares. I have about 3/4 of them, right? So maybe about 4, 5. You say 5? Would it be positive or negative though, Caitlin? Why negative?
It's below.
A region below the x-axis or a definite integral representing the area will be negative. It's just a negative area. What would g of 4 be?
Yeah, I was gonna say 8.
Wouldn't you just refer to that triangle? Area of a triangle would be base times height divided by 2. 4 by 4 divided by 2 would be 8, but it'd be negative though, wouldn't it? Right, Dustin? Goodness, I got to do g of 6 and 8 next. would g of 6 be? I'm going to accumulate more area and go further to the right on the graph of f. It'd be the -8 from earlier, plus about another what? 1, 2, 3, 4. I'd say about 5 or 6 almost. So let's see here. Let's do the -8 plus 6 more. We're adding on more area. I'm accumulating more positive area now. So shouldn't my function values get a little bit less negative? I have slightly more below the x-axis as I do above the x-axis for g of 6. About 8. See, it looks like a trapezoid here. 1/2 the height, so half of 4 times the sum of the two bases. 4 and 4 is 8. Half of 4 is 2 times 8, 16. That's 16 there. The area of this trapezoid would be 16. The height is 4, not 16. 4 and 2 makes 6, so half of 4 is 2 times 6 is 12. I want to say about 12 on that. Half of 4 is 2. Two bases are 2 plus 4, which is 6. 2 times 6 makes 12.
So 4.
-8 and 12 is 4. Here. All the way back to a positive number. Yeah, there's more area above the x-axis than there would be below, right? For x values between 0 and 4, I'd be accumulating a negative area. For x values between 4 and 8, now I'm accumulating more positive areas to go with that negative area from before. That kind of leads into the next question. What x values are the intervals on which g is increasing or decreasing? What are the intervals for x where g is increasing or decreasing? Increasing from 4 to 8. Okay. Increasing from 4 to 8, because aren't I going from -8 to -2 to 4 as I'm adding on the area above the x-axis? I'm accumulating a positive area for this definite interval. Or would it be decreasing? 4. I'm accumulating the area of a region below the x-axis. Am I increasing from 4 to 8 and decreasing from 0 to 4? What happens at 4? Where it changes from decreasing to increasing. If a function goes from going down to going up, what has to happen on the bottom? That's called a part C. Identify any relative extrema. If a function changes from decreasing to increasing, what type of extrema is that? Minimum, right? If you go from going down to going up, how does you rounded the corner on the bottom? If you go from the decreasing, now you're at the maximum. You rounded the corner on top. So that would be at 4, we said? 4 on the -8. Gesundheit. Sketch a rough graph of G. So let's just plot points here. Make a rough sketch by point plotting. Given these values we've got. That's the graph of g of x. At x equals 0, g of 0 is 0. At x equals 2, g of 2 is negative 5. Four, we have negative 8. There's our relative minimum, yeah? I'm going to start going up now, yeah? I'm done accumulating negative area, now I'm going to accumulate more positive area as I've added on the trapezoid on the right part of the graph for function f. At 6, negative 2. And at 8, positive 4. A definite integral gives us the area under the curve. So when I write a function, g of x, that's equal to the definite integral from 0 to x of f of t dt, I'm accumulating the area under function f. G prime of x would simply just be equal to f of x. The derivative, or rate of change of this accumulating area, would be equal to the original function in terms of x. The antiderivative and derivative cancel out.